So another example, in order to find the nth derivative of a function, in this case x multiplied by log x at the point x equals 1. You see, in fact, if you want to find something, if you want to find the first derivative at x equals 1 or x equals 2, it is not a problem. But if you want to find the nth derivative at x equals 1, for example, in fact, you have to find the nth derivative in the general form. So, as for this example, so first of all, you see, you have your y as a product of two functions. So you have to find a derivative of two functions. Do you know this formula? Do you know the formula for the derivative of the product?
Yes,
Yes? Good. Only you?
we just saw in the PDF you sent.
Okay, very good. So you see, I will show you. I think it will be better. It will be better to show you. You see, if I want to find the derivative of a product, yes, it will be the derivative of the first function multiplied by the second plus the derivative of the second function multiplied by the first. Mhm.
Yes, okay.
Okay, good. So we return to our slide. So in this case, you see you have a product of x log x. If I take the first function f of x, which is equal to x, then the derivative of this function will be 1. And I multiply this function by the second one, by the log. Yeah. Then I multiply my first function by the derivative of the second one. The derivative of log is 1 over x. Okay? Agree?
Yes,
Yes, I
agree.
agree.
Very good. So in this case, we have that our derivative is log of x plus 1. Nothing special. Then we proceed exactly as in the previous example. You see, because if I add a constant to my function, it will be exactly the same thing as in the previous example. So I will have that the second derivative will be x to the power minus 1, and so on and so on. So you see, next slide. I can say that my nth derivative is given by this formula. So if you want, you can believe me. You can believe me here, but if you want, as a home task, try. So this formula is our hypothesis. You see? So if you want, you have to try to prove this formula by the method of mathematical induction. Okay? Then if I want to find my nth derivative at x equals 1, I will have something like this. You can check. So an interesting, I think an interesting example is the nth derivative of the sine function. You see here, you have to have some ideas from the trigonometric functions and nothing else, because you see, in fact, the first derivative of sinus is cosinus. But you see, in order to find a general formula for the nth derivative, it is necessary to represent this function cosinus in a special way. In this case, it's not my idea. You see, it's not my idea. So the proposition is to represent this function as sinus of x plus pi over 2. And the same way, you see, if I take the second derivative of my sinus, that is the first derivative of cosinus, it will be minus sinus. So you can check using the trigonometric formulas that it will be sinus of x plus 2 multiplied by pi over 2, and so on. So you see, someone in this exercise or in this work has an idea how to represent the nth derivative of the function sinus, and the formula is like this. So as a homework, you can check this formula by the mathematical induction. Okay?
Okay.
Very
Okay.
good. So the next example is to find all the derivatives of the function 1 over x. You see, in this case, like in the previous one, we make use of our table of derivatives. And I repeat here that the derivative of a function x to the power alpha is alpha multiplied by x to the power alpha minus 1. In this case, we suppose that x is strictly positive. Why? Because we cannot consider square root, for example, uh, of a negative x. Okay, you see. Then, if you take the first derivative, then using the formula 3.3, the second derivative, finally, you have some idea. The idea is here. So the nth derivative, due to our third, fourth derivative, the general idea, the general hypothesis is like this. So the home task for you, if you want, please check this formula by the method of mathematical induction. Okay?
Okay, sounds good.
So now, the last topic here, but rather important, is, I don't know, do you know something about the function defined parametrically from your lectures?
Yes, we know something about it.
You know something about. Very good. So you see, roughly speaking, I have something like x. You see formula 4.1. I have something like x, which is defined using a parameter t, and I have something like y, defined like like a function defined in terms of the parameter t. So you see, if it is possible, to find a parameter t in terms of x from the first equation, you see, I will have that y is the function of x. Yes?
Okay.
Eric, is it clear?
Yes, it's clear.
Because you see, it is not easy to find t as a function of x usually. That is why a lot of curves are defined parametrically, like this equation 4.1. So you see here in this slide, you have an example. So in fact, you can parameterize the circle. If you put that x is capital R cosine st and y is R sine st. You see, in this case, it's a simple thing. So if you take x squared plus y squared, then you have really the equation for a circle with radius r. Clear? Is clear?
Yes, it's clear.
So the last slide in this case, you see, we have, you will read this, but in general, In general, what I want to say, if I can explain in some way my parameter or my variable, in this case, t, is a function of the variable x, I will have a composite function. You see, y of x is the formula 4.3. So I will have my function y, but not as a function of t, but already as a function of x. You understand this?
I understand.
Valentina, is clear.
Yes, for now is clear. I need
So-
to review something, but it's clear.
No, Valentina, if you have some questions, please. So the idea, you see, under some conditions, you will read these conditions. Okay? Under some conditions, maybe we have a chance. Maybe it is possible to represent our parameter t as a function of the variable x. You see? Then it is possible to write that our function y is in
Did I
fact
tell you or not tell you that today we were going? And I said to do them.
questions, excuse me. It's the last slide. You will be free. So it is possible to write our function y as a function of the variable x. Then you see, we know that by the theorem of the inverse function, by the formula 4.2, we can find the derivative of my function or my variable t with respect to x. You see this formula 4.2. So in this case, I repeat the formula of the derivative of the inverse function. You see? Then, you see, if I have that finally, my function y is the function of x, but in fact, you have that y is a composite function, y of t of x. You see? Then, using this formula 4.2, first of all, we have to use the chain rule. You see, I use the chain rule. So I take my derivative with respect to t, so the argument of my function, t, and then the derivative of t with respect to x. That is, finally, I will have my derivative y with respect to x as y with respect to t over x with respect to t. So we have no problem. You see, in this case, I want to find the derivative with respect to x, but this derivative is reduced. I know this x is x of t, y is y of t, so I can find easily the derivative of my function y with respect to x. Is it clear?
Yes, it's clear for me.
Yes, it's clear.
Clear. So I think it will be enough for today. So I propose you. I hope we will send you something like a program. I will discuss this with the lecture. Yeah. And then you will have something like a program. Okay.
Okay, sounds perfect.
So have a good evening if it is possible.
And you too,
with-
Professor.
Thank you very much. So once we have a program, maybe we can talk if will be possible. Okay.
Yeah, okay, of course.
So see you. Ciao.